everyone. Just think of a scenario to build a house. In that case, you have to decide how many rooms you need, where to place them, and what materials to use, and many more questions. Designing AI models is also similar. Instead of manually selecting layers and connections, Neural Architecture Search NAS automates the process, like a smart architect designing the best house. This helps create faster, more efficient AI models for tasks like image recognition and speech processing and many more. Let's explore how NAS makes AI smarter. Coming to the definition, Neural Architecture Search or NAS automates the design of neural networks, replacing the traditional trial and error approach. Instead of manually selecting layers and connections, NAS explores different architectures to find the best one. It uses different techniques like reinforcement learning and optimization to create efficient models with high accuracy, saving time and efforts in AI and development. The question is why NAS is important. Manual design of deep learning models is time consuming and suboptimal. NAS helps in discovering architectures that are optimized for both accuracy and efficiency. The mathematical approach to NAS. NAS can be formulated as an optimization problem where we search for the best architecture A that maximizes the performance metric M of A. Now we can simplify this a little more. Like search space, that is A, it represents all possible architectures including different layer types, connections, activation functions. Next is search strategy. Determines how we explore different architectures in A, that is random search, reinforcement learning, evolutionary algorithms. And we are trying to find M of A, that is performance evaluation, which measures how well an architecture performs, typically using accuracy, latency, or a composite metric. Neural architecture search has three key components. First is search space. It defines possible architectures including layers, kernel sizes, and activation functions structured as a graph. Search strategy. It explores architectures using methods like random search, reinforcement learning, evolutionary algorithms. Third is performance estimation. It evaluates architectures with full training, weight sharing, or surrogate models like the predictive metrics. Let's implement a simple NAS system in Python that can search for the best model architecture using random search. We're going to use the MNIST dataset for digit classification. First, we are going to load the MNIST dataset, which consists of handwritten digits from 0 to 9. In this step, first we are loading MNIST data. We are reshaping input images to 28 by 28 into 1 grayscale format. We are normalizing pixel values to the range between 0 to 1. And lastly, converting labels to one-hot encoding for the classification purpose. Second is defining the searchable architectures. Here we define different functions. The simple model has one convolution layer, while the complex model has an additional convolution 2D layer. Both models use ReLU activation function and max pooling to reduce the dimensionality. We then flatten the output and pass it through dense layers for classification purpose. Next, for train and evaluating the models, we define a search space containing different architectures. We train each model for 3 epochs and evaluate its accuracy on the test set. The model with the highest accuracy is selected as the best performing architecture. In short, it iterates over different architectures and trains each for 3 epochs, evaluates accuracy on the test set. It keeps track of the best performing model. Finally, we print the best model and its accuracy. This demonstrates how NAS can help automate model selection by systematically testing different architectures. This is how neural architecture search can automate the model selection process. Performance of an architecture A is measured using cross-entropy loss, where L of A is the loss function for architecture A. NAS techniques vary in efficiency and cost. Random search is simple, but it's inefficient. Reinforcement learning finds optimal models with rewards, but it is computationally very expensive. Evolutionary algorithms evolve models over generation, but it can converge very slowly. Gradient-based NAS or DARTs, these are very efficient, but it may go to the suboptimal solutions. Each method balances accuracy, speed, and cost, which is quite helpful. Advanced NAS methods like RL and DARTs provide better results. Neural architecture search is widely used in deep learning applications, including image classification, object detection, and natural language processing. It enables AI researchers to develop optimized models with minimal manual intervention. With NAS, we can efficiently explore different architectures and find the most optimal model for any task. In summary, as AI models grow in complexity, NAS will play a crucial role in discovering architectures that balance performance and computational cost. So happy coding!